Okay, today I would like to present a project video anomaly detection. Uh, the motivation of video anomaly detection system is that CCTV is widely used in surveillance system, but for post-event analysis only. And the CCTV recordings still need to be analyzed by human worker. So an intelligent system that can analyze real-time events should be designed to automate the human task. Nowadays, there are four main challenging factors in designing anomaly detection and localization. The scene complexity, time complexity, dataset availability, and object localization performance. The figure in the right shows the relationship between scene complexity and time complexity. As we have the more complex, more crowded scene, the system will require more time to analyze the scenes. The problem definition, as we we want to design video anomaly detection system, so the main objective of modeling is to detect the video anomaly by maximizing frame level and pixel level performance and minimizing the false alarms. And the input to the model is a sequence of video and outputs are frame level and pixel level anomaly scores. And based on the assumptions that the frame corresponding to the anomalous events rarely occur with significant deviation in appearance and motion features from the normal events. So based on this assumption, one can apply the unsupervised learning method for anomaly detection. This slide shows the implemented method, which is Deep Spatio-Temporal Translation Network, or DSTN, that published on IEEE Access. There are several frames used for feature collection in this framework. The first one is the original frame and the background removable frame and the dense invert search optical flow frame. At first, the background removal frame and the DIS optical flow frame are fused into the fused then optical flow. And the patches of the original frame and the background removal frame will be concatenated and fed into the generator, and the generator will generate the generated dense optical flow. So now we have the fuse and the generated dense optical flow in the training process of the GAN. This tool will be used. In the GAN, there are generator and discriminator. The generator will try to generate the optical flow that are similar to the real one, which is the fused optical flow. And the discriminator will try to discriminate between the generated and the fused, or discriminate between the real and the fake samples. They will iterate like this until the generator will generate the optical flow that's similar enough to the target. Additionally, in training, the input is only the normal events, and when test time, if we put the abnormal sample to the model, the generator will not generate the optical flow properly because it's not trained on the abnormal sample. So at the differentiation module, we subtract the fields, one with the generated optical flow. So the output of differentiation module will have high value, and those high value regions uh, indicate the abnormal objects. And the edge wrapping module is pre-processing step that uh, try to wrap the redundant edge in the output frame of the differentiation module. So the output will be more more clear. The abnormal region will be more fit to the object edges. And take a look at the result. This is a ROC comparison on the UCSD PET1 dataset. This is the frame level performance. The blue line is the STN. We can see that it outperforms all other several methods. And take a look at the corner. The STN can reach high true positive rate at the lower false positive rate than other method. And the pixel level performance. Uh, this part is obvious. The STN is outperform other method. And the right figure is on the UCSD PET2 at the frame level. Again, the DSTN, take a look at the corner, have high true positive rate at lower false positive rate than other method. Uh, this slide show the impact of edge wrapping. The first row is without edge wrapping. We can see that the abnormal region is very very large and redundant and not fit to the object edge, right? And the bottom row with the edge wrapping, the abnormal region is more fit to the object edge. So the conclusion is that the DSTN method is based on reconstruction of optical flow of the normal events, and the edge wrapping helps improve pixel level performance. And the last one, building real-time accurate video anomaly detection system is still challenging due to complexity in real scene, hardware requirements, dataset availability, and localization performance. Thank you.